Let A is equal to R minus 3 and B is equal to R minus 1. Consider the function defined from A to B, where A is a domain and B is codomain, defined by f of x is equal to x minus 2 upon x minus 3. So here x is not equals to 3, that is R minus 3. We have to show that f is 1 to 1 and onto. For 1 to 1, so 1 to 1 definition, let me write here. We have two cases to prove it. F of x1 is equal to f of x2 implies x1 is equal to x2. This is how we can prove it. Or else another definition, for x1 not equals to x2 implies f of x1 is not equals to f of x2. So let us consider for 1 to 1. First definition, let us consider f of x1 is equal to f of x2. Consider f of x1 is equal to f of x2. So we can write x1 minus 2 upon x1 minus 3 is equal to x2 minus 2 upon x2 minus 3. So cross multiplication, x1 minus 2 into x2 minus 3 is equal to x2 minus 2 into x1 minus 3. So on simplification, x1 x2 minus 2x2 minus 3 times of x1 plus 6 is equal to x1 x2 minus 2x1 minus 3 times of x2 plus 6. So on simplification, x1 x2 x1 x2 on same on both the sides with the same sign gets cancelled and 6 also gets cancelled. The remaining terms we can bring minus 3x1 and here it is plus 2x1 is equal to, and here we can write minus 3x2 and plus 2x2. So we can write minus x1 is equal to minus x2 or x1 is equal to x2. So we got the condition for f of x1 is equal to f of x2, x1 is equal to x2. So we can say that f is 1 to 1. So the first function, the function given function is 1 to 1. And now and coming to the next onto. So the definition of onto says if codomain function that is b is equal to range of function that is y or f of x. If we can prove that the range of the function is codomain that is b r minus 1, we can say that the given function is onto. So now let us consider y is equal to f of x, which is equal to x minus 2 upon x minus 3. So on cross multiplication, we can write xy minus 3y is equal to x minus 2, or we can write xy minus x is equal to 3y minus 2, or x taken common y minus 1 is equal to 3y minus 2, or x is equal to 3y minus 2 upon y minus 1. Clearly we can say that the y cannot be equal to 1. Y cannot be equals to 1 means y belongs to r minus 1. Since for every y belongs to r minus 1, there exists second, right? For every y belongs to r minus 1, there exists x belongs to r. We have some real number except 3 such that f of x is equal to y. And here we can say that r minus 1 is nothing but your codomain. So here range is equal to codomain, and hence we can say this function is onto. So f is 1 to 1 and f is onto, so hence proved. Let R be the relation on set of integers Z defined by R is equal to A comma B such that A and B belongs to Z integers and mod of A minus B is less than or equals to 5. And the difference between any two numbers is always lesser than or equals to 5. And we need to check that this relation is reflexive, symmetric and transitive. And we know that the relation is said to be reflexive if for every A belongs to A comma A must belongs to the relation R. For every element in the set, if A comma A belongs to the relation, then we can say the relation is reflexive. And coming to the symmetric, if A comma B belongs to R, then B comma A belongs to R for A comma B belongs to the set A. If A is related to B, then B is also related to A, then we can say that the relation is symmetric. And coming to the transitive, if A is related to B and B is related to C, if these both ordered pairs are there in the relation, then there must be A comma C belongs to the relation R. Then we can consider that the relation is transitive. So let us check here for this relation R is equal to, it is given ordered pairs A comma B, we can write A comma B belongs to R where mod A minus B is less than or equals to 5. And for reflexive, we can say that for every integer, for every A belongs to Z, A minus A, that is mod, even if you apply mod, it is 0, which always lesser than or equals to 5. So we can consider that for every A belongs to Z, for every A belongs to Z, A comma A, we can say that A comma A belongs to the relation. For every A belongs to Z, A comma A belongs to the relation R, and hence we can say the relation is reflexive. So we can say R is therefore relation R is reflexive. And coming to symmetric, coming to the symmetric, let us consider let A comma B belongs to the relation. So which implies that if an ordered pair is belonging to the relation, then it must satisfy mod of A minus B is less than or equals to 5. And we know that mod of A minus B or mod of B minus C will give the same result because the modulus is applied. So mod of B minus C is less than or equals to 5. So here the elements are interchanged here B minus A. We can also say that B comma A, an ordered pair must belongs to R. So for A comma B belongs to R, we got B comma A belongs to R, and hence we can say that this relation is R is symmetric. So we got the second one, R is symmetric. And coming to the third one we'll consider an example for R is transitive or not. Let us consider an example. Let 1 comma 3 belongs to R since 1 minus 3 mod, that is negative 2 or 2, modulus of negative 2 is 2, which is less than or equals to 5, and 3 comma, so we can consider 3 comma 8 and one more ordered pair 3 comma 8 belongs to R, which implies mod of 3 minus 8 is negative 5, mod of negative 5 is 5, less than or equals to 5, which is also true. So 1 comma 3 is satisfying the relation and 3 comma 8 is also satisfying the relation. But 1 minus 8, if we can see, which is modulus of negative 7, that is mod 7, modulus of negative 7, 7 which is not less than or equals to which is greater than 5. So we can say that 1 comma 8, here 1 comma 8 does not belongs to the relation. So for A comma B belongs to R and for B comma C belongs to R, but A comma C, this 1 and 8 does not belongs to R. 1 comma 8 is not belonging to the relation, and with this example we can say R is not transitive. So to disprove it, we need to give at least one example. So here one example is enough to show that this relation is not transitive. In general cases, we will prove it, but in the case of not correct, we need to give a counter example. Using matrices, solve the following system of equations. 4x plus 3y plus 2z is equal to 60. X plus 2y plus 3z is equal to 45. 6x plus 2y plus 3z is equal to 70. So the given equations we can write in matrix form as taking the coefficients 4, 3, 2, 1, 2, 3, 6, 2 and 3 from the three equations of the right side, and the variable matrix we can write here x, y, z is equal to, and the constant 60, 45 and 70. It's a column matrix. So we can write in the form of Ax is equal to B, where A is the coefficient matrix, X is the variable matrix and B is the constant matrix. And we know that X is equal to A inverse into B. This is matrix inversion method. Matrix inversion method, and this method is applicable only when A inverse is existing. That is delta is not equal to 0. Because we know that A inverse is equal to 1 by delta into adjoint of a matrix A. So let us find the determinant of the matrix. Det A is equal to determinant of the coefficient matrix, that is 4, 3, 2, 1, 2, 3, 6, 2, 3, which is equal to 4 times of 2 3 is a 6 minus 6 0, minus 2 3 times of 1 3 is a 3 minus 18, that is negative 15, and again here plus 2 times of 2 minus 12, that is negative 2. So which is 45 minus 20 is equal to 25, not equal to 0. So we can say A inverse exists. If A inverse exists, we need to find 1 by delta into adjoint of A. Its matrix inversion method is applicable, we can write. Now to find the adjoint, let us use the shortcut method to determine the adjoint. So consider from the coefficient matrix second row second column elements, say from 2. So 2. So we can write starting with second row second column element 2, and then continue, the next number is 3 in the same row, and then again come back to the 1, then end up with again the same element from second row second column element. Similarly continue with the next row, that is starting with 2, 2 and then with the 3, then 6 and again 2. So we can write here 2, 3, 6 and 2, and coming to the first row again 3, 2 and again 4 and then 3. So I can write here 3, 2, 4 and again 3, and again come back with the same numbers 2, 3, 1, 2, second row second column. And now we will write the adjoint here. Adjoint of a matrix is actually transpose of the cofactor matrix. So I can write here finding the calculation determinants 2 3s are 6 minus 6 0, 2 2s are 4 minus 9, that is negative 5, 3 3s are 9 minus 4, it is positive 5, And coming to the next one, 3 6 are 18 minus 315. Here performing column wise and writing here row wise, because transpose matrix we need to apply here. So 3 4s are 12 minus 12, it's a 0. 2 1s are 2 minus 12, that is negative 10. And again the last one, so we can write here 1 2s are 2 minus 12 minus 10. 6 3s are 18 minus 8, it's a plus 10. And 4 2s are 8 minus 3, it's a 5. So adjoint of a matrix is equal to, we can also take 5 common, and we can write 5 times of 0 minus 1 plus 1, 3 0 minus 2 minus 2 2 and 1. Okay, so now we know that A inverse is equal to 1 by delta into, that is 1 by 25 times of 5 times of 0 minus 1 1, 3 0 minus 2 minus 2 2 and 1, which is equal to 1 upon 5 times of 0 minus 1 and 1, 3 0 minus 2 minus 2 2 and 1. And now the variable matrix X is equal to A inverse into B. So we can add 1 upon 5 times of 0 minus 1 1, 3 0 minus 2 minus 2 2 and 1, multiplied with the matrix B, that is 60, 45 and 70. So on simplifying, you will be getting 1 upon 5 times of, so 0 into 60 is 60, minus 1 into 45 minus 45 plus 70. So we can write minus 45 plus 70. So here minus 45 plus 70 is 25, and 360s are 180, 180 and minus 140 is 140 here, and here minus 120 plus 90 minus 30 plus 70 is 40. So 25 upon 5 is 5, 40 upon 5 is 8, and 40 upon 5 is 8. So the variable matrix X is equal to, we can write X Y Z. So X is equal to 5, X is equal to 5, Y is equal to 8, and Z is equal to 8 is the solution by matrix method. So let us also verify by substituting in any one of the equation. Second equation, let me substitute 5 plus 2 into 8 16 plus 3 into 8 24, 24 plus 16 is 40, 40 plus 5 is 45, satisfying. So we can say that this is the solution. Using integration, find the area of the region bounded by the lines y minus 1 is equal to x, that is y is equal to x plus 1, and the x-axis, and the ordinates x is equal to negative 2 and x is equal to 3. So let us mark them, the graph, x-axis and y-axis, the origin, and we know that y is equal to x plus 1 line passes through minus 1 comma 0 and 0 comma 1. So let us take the line. This is what the line, y is equal to x plus 1, and the lines x is equal to negative 2, x is equal to negative 2 will be here, and x is equal to 3 somewhere here, and the area bounded along with this line between the x-axis and the line is here, and this is what the shaded region. we need to find the area of this region by using integrals. So let us mark the points. Say this is A, B, C, D, E. Say this is F. So we need the area. Required area is equal to area of the figure BAC plus area of the region ADEA. We can write ADEA. Now by using the integrations, we can use from B to A. So from minus 2, this is x is equal to minus 2 and this x is equal to minus. From minus 2 to minus 1, mod y dx plus integral minus 1 to 3 plus 3 y dx, because it is below the x-axis from minus 2 to minus 1, so we need to apply the mod. So we can write here integral minus 2 to minus 1, mod of y is nothing but we can apply here mod of x plus 1 dx plus integral minus 1 to 3 x plus 1 dx, and mod of x plus 1 value, mod of x plus 1 value will be, we can write x plus 1 when x is greater than minus 1 and negative of x plus 1 when x is less than minus 1. So we need to apply here from minus 2 to minus 1, it is below minus 1. So we can write here integral minus 2 to minus 1 negative of x plus 1 dx plus integral minus 1 to 3 x plus 1 dx. Let us simplify here. Let me write here. So let me write here, which is equal to minus 2 to minus 1 negative of x plus 1 dx from minus 1 to 3 x plus 1 dx, which is equal to minus x square by 2 minus x over the limits minus 2 to minus 1, and again here x square plus x over the limits minus 1 to 3, which is equal to minus 1 by 2 plus 1 minus lower limit minus 4 by 2, that is minus 2 plus 2, and again the next plus 9 plus 3, sorry this is by 2, 9 by 2 plus 3, and again the lower limit is 1 by 2 minus 1. So on simplifying we can write 1 minus half is half, and again minus 2 plus 2 is 0. So 9 by 2 plus 3 is 15 by 2, and again here 1 by 2 minus 1 is minus half, that is plus half. So 16, 17 upon 2, 17 upon 2 is 8.5. 8.5 square units is the required area. So the answer is 8.5 square units. Find the foot of the perpendicular drawn from the point 1, 6, 3 to the line x upon 1 is equal to y minus 1 upon 2 is equal to z minus 2 upon 3. So from the point the foot of the perpendicular upon the line x minus 0 upon 1 is equal to y minus 1 upon 2 is equal to z minus 2 upon 3. Let us consider M be the foot of the perpendicular. So generally we can consider any point on the line as x minus 0 upon 1 is equal to y minus 1 upon 2 is equal to z minus 2 upon 3 is equal to say lambda, so that we can simplify here. X is equal to lambda y minus 1 is equal to 2 lambda, z minus 2 is equal to 3 lambda, that is x is equal to lambda, y is equal to 2 lambda plus 1, and z is equal to 3 lambda plus 2. So general point on the line, general point on the line, say m lambda 2 lambda plus 1, 3 lambda plus 2. Now the direction ratios of the line joining P and M are, we can say, lambda minus 1, 2 lambda plus 1 minus 6, 3 lambda plus 2 minus 3. That is lambda minus 1, 2 lambda minus 5, and 3 lambda minus 1 are the direction ratios of the line. And we also know the direction ratios of the given line. The direction ratios of the given line are 1, 2, and 3. The denominator we have. Say these are A1. Let us consider A1, B1, C1, and here let us consider these direction ratios are A2, B2, and C2. Since PM is perpendicular to the line, since PM is perpendicular to line, we can say that A1, A2 plus B1, B2 plus C1, C2 is equal to 0. So we can write here A1, that is 1 times of lambda minus 1 plus 2 times of 2 lambda minus 5 plus 3 times of 3 lambda minus 1 is equal to 0. On simplifying, we will get lambda minus 1 plus 4 lambda minus 10 plus 9 lambda minus 3 is equal to 0. That is 9 plus 4, 13 plus 1, 14 lambda. 14 lambda minus 14 is equal to 0. That is lambda is equal to 1. So that we can consider the point or foot of the perpendicular point M as 1 comma 2 into 1 plus 1 comma 3 into 1 plus 2, which is 1 comma 2 ones are 2 plus 1 3, 3 ones are 3 plus 2 5. So we can say the foot of the perpendicular is 1 comma 3 comma 5 is the answer. Find the shortest distance between the following pair of lines and determine whether they intersect or not. X minus 5 upon 4 is equal to y minus 7 upon negative 5 is equal to z minus of minus 3 upon negative 5, and another line x minus 8 upon 7, y minus 7 upon 1 is equal to z minus 5 upon 3. So these two lines are, this line is passing through the point 5 comma 7 comma minus 3. So let us consider the vector passing through the point whose position vector a1 is equal to 5i plus 7j minus 3k, and this line having the direction ratios 4, minus 5, and minus 5. So let us consider the position vectors of this direction ratios as b1 vector is equal to 4i minus 5j minus 5k. Similarly, for the second line, the second line is passing through point 8 comma 7 comma 5. The position vectors, let us consider a2 is equal to 8i plus 7j plus 5k, and having the direction ratios the direction ratios 7 comma 1 comma 3. So let us consider the vector b2 is equal to 7I plus j plus 3k. And now we can also say that the direction ratios, they are not proportional, b1 and b2, and hence we can say they are not parallel, which implies that they are intersecting. So the shortest distance between the lines shortest distance between the lines passing through the points a1 and a2 and having the direction ratios b1 and b2 respectively can be taken as a2 minus a1 dot b1 cross b2 upon mod of b1 cross b2, the whole mod. So let us find a2 minus a1. So a2 minus a1 is equal to 8 minus 5, that is 3I, 7 minus 7, that is 0j, and 5 minus of minus 3, that is 8k. This is a2 minus a1 and mod of b1 cross b2. Let us find b1 cross b2. b1 cross b2 vector is equal to I, j, k. b1 vector 4 minus 5 minus 5, and b2 vector we can add 7, 1 and 3, which is equal to I times of minus 15 plus 5, that is minus 10, minus j times of 12 plus 35, that is 47, and plus k times of 4 plus 35, that is 40. 4 plus 35, that is 39. 39. So we can write b1 cross b2 vector as minus 10I minus 47j plus 39k, and mod of b1 cross b2 is equal to under root of minus 10 whole square plus minus 47 whole square plus 39 whole square, which is equal to the root of, we can write here 3830. After simplification we got the value 3830. So therefore the shortest distance between these lines is equal to mod of a2 minus a1 is 3I plus 0j plus 8k dot b1 cross b2 is minus 10I minus 47j plus 39k divided by root of 3830. After further simplification we got it. So minus 30, and here it is 39 8 times. So 240 plus 72, that is 312, divided by root of 3830, which is equal to 312 minus 30 is 282. So we can say 282 divided by root of 3830 is the answer. The shortest distance is 282 upon 3830 is the answer. And also we can conclude that since the direction ratios are not proportional, and hence we can say that they are skew lines which are not intersecting. So these lines are not intersecting because they are not parallel.